Okay. I should find the statement that I want to show. Okay. So theorem one. We consider the set of partitions. Let's say partitions mu and mu, where a partition mathematically is just a weakly decreasing chain of non-negative numbers, whose sum up to a certain integer. Okay, and that integer is said to be partitioned into these. Okay. So there, mu is a partition. This is arbitrary. And mu is a partition satisfying the following strange property. The parts differ. Maybe I'll introduce the Young diagram of a partition. So let's say we have a partition, 5 to 1 of 8. I didn't calculate wrong. And the Young diagram consists of 5 boxes, and 2 boxes, and then 1 box. Okay,
I can't believe that put his name on this.
I agree. Yeah. So this has mu has the strange property that each successive row, this length has to be greater than or equal to 2. So you cannot decrease by 0, and you cannot decrease by 1, which are the only other options besides greater than or equal to 2. Okay. And furthermore, the smallest part also has to be bigger than or equal to 2. So mu has this special type of shape. Okay. And we also consider triples of partitions pi, rho, and C, where pi is a partition into pieces that are 1, 2, and 3 mod 5. Okay. Rho is a partition into pieces that are 2, 3, or 4 mod 5. And C consists of things that are 0 mod 5. Okay.
Are there any relationships between these 5 partitions?
There are.
As in, are they all partitions of the same integer?
I will write the last line. So the theorem is that there is a bijection between the set of such mu's and mu's and the set of such i's, rho's, and c's, such that for all n, where n is equal to the total sum of mu plus the total sum of mu, and n is equal to the total sum of pi, the total sum of rho, and the total sum of c. So for any n, there are a bunch of mu's and mu's whose total sums are n, and there's a bunch of pi, rho's, and c's satisfying all the relevant conditions. And this is saying that there is in fact a bijection. And so in particular, they're the same number. I think it might be insightful to do an example. But let's try n is equal to 3. Okay. So what kinds of mu's and nu's are there? So let's have this side be the mu and nu side, and this be the pi, rho, c side. Okay, so what's on what side?
There seems to be only one pair on the left side, right? Because nu needs the smallest piece to be bigger than or equal to 2. the smallest piece.
So
Sorry, there must be two things.
okay, so nu can be 2
Uh-huh.
and nu can be 1.
Right. Or nu can be 3, and I guess mu could be empty.
Yeah, nu can be 3, and there's no other choices for nu, right?
Right.
Okay, so that seems to be what's on the left-hand side.
So on the right-hand side, on the C's.
I think also we do allow the empty.
Okay.
We do allow the empty set here.
In which case, mu can be any partition of 3, of which there are 3.
Of which there are 3.
Yeah.
There's
3, just 3. And then there's, yeah, you turn that on its side. And then there's 2 in them. Yeah.
Let's double check. I think this is right. So there's a total of 5, right?
Mm-hmm.
Okay, so let's check the right-hand side.
C has to be empty all the way through.
I agree.
Row can only be 2 or 3.
Okay, so row like this or like this.
Is row allowed to be empty?
I don't think so. Because 0 is 0 modified.
I see. In which case?
And pi, what's available for pi? Well, in this case, it's
1.
1.
Or empty.
Empty.
Wait. If pi is allowed to be empty, why can't row
No,
be?
row cannot. Like, wait, something's gone terribly wrong. Okay, I think you're right. Or empty. Then we open up a lot more possibilities.
Well, if row is not empty, these are the only 2 options, right? Nonetheless, C has to be empty no matter what.
Yeah. So let's consider the case that row is empty.
Right.
And then there are
yeah, it's
all of those.
It's a copy of the 2 rows are identical. It's just we've added a bunch of empties.
Yeah. Okay, so a rather trivial case.
Yeah.
But at least, it seems to work out, allowing degenerate situation. It's I think quite mysterious why 5 is the main character in this theorem.
Yeah.
There's also
knowing the pentagonal.
I agree. That's definitely a little suspicious. Though actually in the proof of the pentagonal number theorem, 3 is the main number.
Really?
Yeah, it's a little
very suspicious.
Yes, there's another theorem. It's called the Ramanujan congruence. Ramanujan congruence. I spelled that wrong. It's fine. Which says that phi of 5n plus 4 is congruent to 0 mod 5 for all n. And also phi of 7n plus 5 is congruent to 0 mod 7. And also phi of 11n plus 6 is congruent to 0 mod 11 for all n. And in fact, these are also quite mysterious.
I thought you were going to say something absolutely insane.
Unfortunately.
I thought you were going to say something like these are the only congruences.
They are actually.
Is this
a theorem? For a certain these are particularly nice congruences. There are similar ones that hold that are less nice, but these are the only nice ones for some definition of nice that I don't remember.
Is that a provable fact, or is it like
provable?
Oh my gosh.
Yeah, and there are nice proofs of these that I would like to present some other day. Anyways, let us return to this bijection. Okay. This is a combinatorial statement of what's called the Rogers-Ramanujan identities. In particular, the second of the Rogers-Ramanujan identities. Okay, let's get down to work. Okay. The general strategy that the proof goes through is it bijects this mu pair with something called a cylindric partition. And then they biject those with triples, pi, rho, and c. So now is the time to talk about cylindric partitions. So we will have a run example. And the run example will be the following guy. It goes 10, 8, 4, 3, 3, 10, 5, 1. Okay. Rather mysterious. And we will only be focusing on cylindric partitions of this shape. Okay, so 3 up and then 2 right. What does that mean? Well, if I go 3 up again and then 2 right again, I can copy paste these numbers up here. So I get 10, 8, 4, 3, 3, 10, 1. And note that this decreasing property going to the right and going down remains true. That's what makes it cylindric. Okay, so if I copy paste this block according to this 3 up, 2 right pattern, then I actually create the ends of this copy naturally extend this copy. Okay, so the paper calls this column tau 1 and this column tau 2. And there's also a notation W, 0, 0, 0, 1, 1, corresponding to 0, 0, 0, and then 1, and then 1. Okay, so 0 is treated as up, and 1 is treated as right. Okay. There is another way of viewing this this cylindric partition, and it's by looking at the diagonals.
These are also decreased.
These are also decreasing, which come from the decreasing nature of going right and going down. And furthermore, they're interlacing, okay, which also comes from this structure. Right. So if I put 4 in the middle here, then it is. And I put 8 and 1 in between, it goes 10, 8, 5, 1, and so forth. And these interlace. So it's written like so. So 4 is funky less than 8, 1 is funky less than 10, 5.
It's an elementary substructure.
Unfortunately not. Maybe that'd be easier to understand. And then it flips. Okay, because it interlaces the other way. Which funky less than 3. Okay. And these guys are called lambda 1 all the way to lambda 5. These will become relevant later. And they're interlacing. Okay. Okay. The first thing we'll do is go from a cylindric partition.
Sorry, really quick. What is the relationship between the cylindric partition and N?
I'm actually not sure. We'll find out.
I see.
To mu and mu. Okay. I think it might be that the total sum of each block is equal to N.
Tower, maybe.
Yeah. And this is the way we do it. It is a little convoluted. And the idea is to create a layer cake decomposition of sort of slices from this axis. So imagine we have 10 blocks flying out of the board like this, 10 blocks out of the board, 8 blocks out of the board. And then we just cut this thing with like cuts in this orientation. So layer 10, it will just be these 2 blocks. Okay. Layer 9 will also be these 2 blocks. Okay. Maybe I'll write it like this. Layer 10, these 2 blocks. Layer 9 is also these 2 blocks. Okay. But then when I hit layer 8, now this guy comes in. Layer 8. I get a footprint that looks like this.
Mm-hmm.
And in fact, it remains like that for layer 7 and layer 6. And then layer 5, now I get that guy. He shows up in the layer cake. Let's keep going all the way down. Layer 4. Have this situation. No. Layer 3. I get these extra guys. Did I miss it? Layer 2 is also that. And finally, layer 1, you have everybody. And so there are 2 cells here, 2 cells on layer 9, 3, 3, 3, 4, 5. Interesting. Okay. The next step is we have a flag, which is either 1 or 2. Okay. And the way that flag works is 1, if the shape looks like this, where there's this component is less than or equal to 1. Okay. Notice that all the shapes have to look like this because of this decreasing. Yeah, it always has to be longer on the left. Right. And 2, if this length is greater than or equal to 2. Okay. And finally, note that by nature of W, which describes 3 up and 2 right, we can only get the following shapes. We can only get this. We can get by which I mean there's a 0 extension here, or a 1. Okay. We can also get something of length 2, and then we can also get something of length 3. But we cannot get something of anything longer than that. Why is that the case?
If we got something of length 4, then one of the 2 bottom guys would be bigger than, yeah, it wouldn't be decreasing.
That's right.
On the second row.
That's right.
In the step.
Yeah. So a careful study of the cylindric nature using this 3 up, 2 right pattern reveals that these are the only possibilities. And these are flag 1, and these are flag 2. Yeah. Okay. And furthermore, there are even number of blocks in this one and this one, and an odd number of blocks in this one and this one. Okay. This will be important later. So let's calculate the flags for all of these. It should be trivial. Okay. So this one is flag 1, 1, 1, 1, 1, 1, 2, 2, 3. Okay. Any question? Now let's go over here.
This is feeling very mod 4.
I agree. I agree. It is a complete mystery where the 5 comes from. There is no hint of a 5 on this. Okay, so let me define for you now what sigma should be. Okay, sigma. That's not any of the letters.
I was wondering why sigma didn't come after the row.
Okay, here's sigma. We just take all of these, and then we put the flag as a subscript. Okay, you can also think about it as a color, right? So this is a 1 colored 2. Okay, and this is a 2 colored 8 or something, blue or red if you get it. Okay, so let's just write everybody down. There's an 8 labeled or flagged 2. There's a 7 with a 2, 7 with a 2, 5 with a 1. Okay, 4 with a 1, 3 with a 1, 3 with a 1, 3 with a 1, 2 with a 1, and 3 with a 1. And there's commas in between all of them. Okay, so that's sigma. We create it by the count, the number of blocks, and also the flag. And from this, we can cook up mu. Actually, we first cook up mu. Okay, so note that the parity here is the same. So 8 has the same parity as 2. Okay. And 5 has the same parity as 1. And 3 has the same parity as 1. And we only take the first one that comes up. So if there's many 3s, which in this case there are, we don't ignore them. And so mu is defined as all the ones whose parities match and come first. So let's see, 8, 5, and 3. Okay. And mu is defined as everybody who's left. So 7, 7, 4, 3, 3, 2. And we keep all the repeats. So there are no repeats in mu, but repeats allowed in
So
mu.
what counts as part of the data of a cylindrical partition? Is it the W and the tau 1 and the tau 2?
That's right.
Okay.
Yeah. Or equivalently, it's the W and the lambdas, which are the diagonals.
I see.
You can reconstruct either one, each representation from you.
Okay. And are the flags, do they depend on the W, or is it the same rule for determining the flags?
In this case, in this specific setting, we have this situation of flags. I'm not sure if any of this generalizes past W is equal to 0, 0, 0, 1, 1.
Okay.
The first Rogers-Ramanujan identity comes from another such W, but it's like a different construction. But in this case,
so I guess I'm thinking, so the set of cylindrical partitions with W equals 0, 0, 0, 1, 1 is in bijection with mu and u?
I'll state the theorem a little more carefully soon.
Okay, sorry.
Yeah. Let's see. Yeah, and also we forget all the flags. Okay. What is obvious is that given given mu and nu, okay, we can cook up sigma. Okay. You just reinstate all the flags, right? And there's enough data here to recover exactly what all the flags were. However, there are a couple of rules for what kinds of sigmas are allowed. What kinds of sigmas are allowed? So here are some rules. First of all, there's no 1, 2. This is impossible because
By observation.
observation. Thank you. Also, if you have an odd number, so k is an odd number, and it's a 2, okay. In other words, the only possible situation is this, okay.
Mhm.
As our analysis showed, the only possible situation is if there's a 3 here. That means that then all appearances of k plus 1 must also come with a 2. Okay, so if you're in this situation and you add 1 block, at best you can get to here.
Right.
And finally, the other situation also is true. If you have an even k, which is labeled a 1, then the only situation is here.
Mhm.
And so therefore, then k plus 1 has to also be 1. Should it appear if it exists? Right. It might not exist based on the layer k decomposition. Okay. Fine. From now sigma satisfying these 2 rules, we can cook up the layer cake decomposition. Okay. For example, if I see 2, which is a 1, then there's only one possible shape it can be, right? It's an even number, so it has to look like this.
Mhm.
And 3 sub 1, well, it has to be in flag 1, and it's odd, so it looks like this. And it just so happens that these are exactly the things that guarantee that you get back something that could be interpreted as a cylindric partition. Okay, so this explains how you get from a cylindric partition to a sigma and to a nu and mu, and also how you get back.
Mhm.
So you get from a mu pair to a sigma satisfying these rules, and the rules we had on mu and nu, or actually the rules we had on mu, since mu was arbitrary, produce exactly sigmas of these
Mhm.
forms. Okay, I actually did not check that in detail, but I think we can take it on stage.
Very believable.
Yes. Okay, that's one half of the story. Okay, the second half of the story.
Oh yeah. Sorry. Yeah. The conditions on nu from the theorem are exactly these 3 rules for sigma. If you interpret this as going back, no 1 sub 2.
It is saying
But a 1 sub 1 is possible, huh?
it's a good complaint. Maybe I'm
Right,
stop
now I'm
believing my
very suspicious.
my statement.
If that's a no 1 sub 1, I would be on board by now.
Very good complaints. Let's see.
If we did the naive thing and we just said nu is the set of guys with opposite parities.
Yes, sounds reasonable, but that's not what
Oh, fish.
the paper says to do. Indeed, this is concerning. This is unfortunate.
What does the paper say?
Let me pause the recording. Okay, so I think that the previous construction works, except we should, instead of taking the things with the same parity flag, take the ones with an opposite parity flag. Okay. And then I will repeat those conditions above. And then we can check that indeed it works. So here 7 and 2 are opposite parity, 4 and 1 are opposite parity, 3 and 1 are opposite parity. So actually the correct mu, I think, should be 7, 4, 2, and mu should be 8, 7, 5, 3, 3, 3. Okay. And again, the rules for sigma are there are no 1 sub 2s, which guarantee that there are no 1s inside of mu, which we wanted. Furthermore, one condition I forgot is that if k sub 1 appears, then all k's have to have flag 1, which is obvious from inspection. If you have a level set of a certain shape, then you cannot have another level set of the same cardinality. And again, if there's an odd k sub 2, which means we're in this situation, then all appearances of k plus 1 must look like this. So every k plus 1, should it exist, must have a flag 2. Every even k sub 1 means that the next k plus 1, should it exist, will also have flag 1. So for example, if there's a 7 sub 2 inside of sigma, can there be a 6 sub 1? Well, no, because then this condition would apply. There's an even 6 with a flag 1, and therefore the 7 would have to have flag 1. Okay. So I think this gives a convincing bijection between cylindric partitions of this spine 0, 0, 0, 1, 1, which is just the data of 2 columns satisfying the cylindric property. Okay. Let's move on to the other half of the bijection. Any questions? Also, let's remember it was 7, 4, 2, and then 8, 7,
5, 3, 3, 3. I have really good memory.
Okay,
You can also see it right in the picture.
that's true. That's true. Okay, let's do the other half, which is unfortunately harder naturally. Okay. I mean, after all, this is the one where this is the half where the 5 starts going up. Okay, so let's get down to business. There will be I'll go through it by example. So let's start with this partition and 8, 4, 3, 3, and 5, 1. Okay, and then 3, 3, 4, 8. And we will do the following moves. Okay, so for every corner that sticks out like this, okay, we will look at these diagonals. So this is where the lambdas come in. And what we will do is that for this guy, we will look at the 2 neighbors. Okay, and then we will subtract the maximum of the 2 neighbors from it. Okay, so if we think about it in terms of a height, right, we have this guy, and then it's a certain column, and then there's a neighbor here, right, and a neighbor here. So let me call this guy lambda, this guy's alpha, this guy's beta. So this diagonal is beta. And then this is lambda, this is alpha, this is beta. Then what I'm doing here is just chopping off the top block or number of blocks. And so here it would be m is equal to 0. I call this value m. And the indexing is super weird. It's based on W. So W goes W1, W2, W3, W4, W5. So actually this is indexed 3 by 4. Let me have a table of the m's. So the m table, put it up here. I have 3, 2, 1, 4, 5. So inside of the 3, 4 spot, I put a 0. Okay. And then I get rid of it. It's gone. I continue along in this column. Sorry, in this diagonal. What I do is I find the minimum of the two guys above it, okay, which would be 8, and the maximum of the two guys below it, which this is 3. And then I do what's called a toggle move. Okay, so right now 5 is sandwiched between 8 and 3. Okay, so 8, 3, and 5, and it's closer to 3 than it is to 8, okay? And the distance is 2. And the toggle move is just to switch it so that it's now at distance 2 from 8. So the toggle move would change 5 to a 6. Okay. Good. Okay. And I actually keep going. So there was a 0 here at some point. I mean, they're all zeros. And on its right and below, it's a 0. Okay. And I also do a toggle move here. Okay. So the minimum above is a 1. The maximum below is a 0. Okay. And so I toggle between the extremes. And so this becomes a 1. So, okay. And finally, here, everybody else is a 0. And so there's nothing to toggle. Okay. We just do that over and over again. That causes, we do everything. Everything that occurs in this block will also repeat in every other block. So,
Is the toggling move only to the left and to the right?
what do you mean?
So in this case, we didn't have to worry about the 10 and the 1 above the what
Yeah,
is now
so
fixed.
yeah, the toggle move is based on the minimum of the two people above it. So if
I see.
there was a 10 here and there was an 8
gotcha.
here, then I would choose
I see.
8. I will do more examples. So the numbers are currently empty. 6, 1, 1. Okay, and there's a empty square here, right? And then a 6, sorry, a 6 is a 6 is here, and this is a 5. No,
it should be 8 and 6.
okay, and sort of some 1s below. Okay, it doesn't end up mattering because the things only involve this. So let me just mark down the original sort of spots. So the original block is sandwiched between these two dots. Let's do the next one. Yeah, this guy. Okay, so this guy, there's an 8 and then a 6 and a 4 around it. Okay, and so I chop off the top 2 blocks. So here m is equal to 2. Okay. M parameter is equal to 2 because it's 8 minus 6. So it goes away. And then we continue our toggling. So this guy, the minimum above it is a 4, and the maximum below it is a 1. So I toggle between the two extremes, it becomes a 4. Because again, I have a 4, 1, and a 1. The distance is 0, and so I need to do something that's distance 0. Okay. Where was I? I was here. I toggle here. Here, the minimum is a 0. That's the minimum number above, and the maximum number below is also 0. So there's no more toggling. Okay, we're done with 2 steps of toggling. Let's keep going. The amazing fact, which I actually didn't look into the proof of, is that it doesn't matter which order in which you toggle. You can toggle any of the open corners, available corners, and at the end you'll get down to something of this shape. And no matter how you do it, you will end up with the same result. Okay, so let's just do it. So let's choose this guy to toggle to do this move by. So 10's here, 6 is here, 3 is here, and so m is equal to 4, which comes from 10 minus 6. There's 4 here, and it's gone now. And I keep toggling along this diagonal. Okay. So here, what's the situation? The minimum now above it is 3, and the maximum below is 1. And so I toggle it, so this becomes a 1. And then I continue here. The minimum above, the smallest guy above is 0, the maximum is 0, so there's no more toggle. Good. Let's toggle which one? It doesn't matter. Choose.
Let's do the 4.
Okay, we'll do this 4. Then m is 0 because there's a neighboring guy of the same height. He's dead.
Rip.
Dead. Wait, I'm toggling this guy now. Okay, so there's a 0 below, there's a 0 here. The minimum is a 3, the maximum is a 0. So this toggles to become a 3. And this guy remains a 0. Okay, no more toggling. Okay. Let's do 6. That's the only open corner left. 6 minus 4 is a 2. Okay. 6 is gone. I continue toggling along this guy. Okay. So here I have 1 is the minimum above and 0 is the maximum below. So I toggle it to be 0. So it actually goes back to 0. It used to be 0. And then there's no more toggling in this item. And the last step is this guy. So m is equal to 1. So 4 minus 3 is 1. And then this guy actually doesn't toggle. There's too many zeros of them. Okay. So this cylindric partition has been chipped away until it's this. Okay, and now all we have to show for it
It's
is
been
this.
defiled.
Yes, yes. Though notice it still remains a cylindric partition of the same spine. Okay. So if we had done this everywhere, then it would have So the correct way of filling this in is put a 3 here, I think. So 1, and that's actually the solution.
It's 310 and then 331.
So because I did not update this.
I see.
This should have been a 1. Yeah. Okay. To my knowledge, this is correct. Any questions? Okay. We do it again. We do it again.
Does it eventually become all zeros?
It eventually stabilizes. And I'll do an example in which it doesn't become all zeros, but stabilizes to something else. Okay. So let's do it again. How should we do it again? Let's just copy over all the data. 3, 1, 0, 0. And everybody else is. Okay, so let's focus on this block. This column. Okay, and now we have a new M matrix. 3, 2, 1, 4, 5. Okay, we got this. 3 and 3. Okay. M is 0 here. This is 0. It's gone. I need to keep toggling. Okay, so what does this toggle to?
1.
Toggles to 1. What does this toggle to? 0. So 0. Okay. Who do you want to do next?
Let's do the 3.
Okay, let's do the 3. So what's
M is 2.
M is 2. It's gone.
The 0 toggles to a 1.
The 0 toggles to a 1. And the zeros below remain 0. Okay. Kill off that guy. Right. M here is 0. There's 1 minus 1 is 0. The 1 is gone.
Everything is on the diagonal, it all stays 0.
It all stays 0. This toggles to 0. This toggles to 0. Fine.
Let's do the 0 first.
The 0 first?
Yeah.
Okay.
Because everything there is
The
0.
0.
It's all 0.
No toggling. Okay. What about the 1? Also is a 0.
And there's no toggling.
Something went wrong.
Oh, fish. Do we need to start over?
Maybe we should start over. We'll start over.
The original configuration was.
I remember. I mean, I have it with 3, 1, 0, 3, 0, 0. Do you agree? That
Yes.
was this mean. 3, 0. Okay, let's try again.
Feel like a senior citizen playing those mahjong tile games.
It is,
It's
you
like,
know.
oh shoot, we got stuck.
This is why this would suck as a geosync, you know, but you know. Okay. M is 0. This toggles to
A 1.
this toggles to a 1. This stays a 0. Okay. Next one. What's the order that we did it in last time? Did we do the 3 next?
We might have.
Okay, let's do the 3 next. Okay, there's a 2 here. And this toggles
to 0.
to 0.
Maybe that's where we went wrong.
I don't know.
Who knows?
We have video evidence of what we did wrong.
I've already forgotten.
Okay, the next one is this guy. M is equal to 0. Okay, so this guy's killed off. This guy
He's surrounded by zeros still. So he stays 0.
stays 0. Better stay 0. Okay. So now this guy's gone.
It should be zeros all the way through, right?
Should be 0.
Everything gets nuked to a 0.
Let's name to a 0. Yeah. So what on earth did we do wrong last time?
I have no clue.
Who knows?
Wait, we did something wrong last time?
Maybe we didn't. Maybe I'm just stupid. Okay.
That's
Okay. Anyways, M is 1 up here.
And
then now it's 0. And now we just get a whole field of zeros.
You're right. This would be a very good thing to animate.
We're finally ready. We have our extremely hard 1Ms. Okay. And also the claim is that we can use these M's to go backwards. In theory, this is possible because toggling is a reversible operation, right? It's you just use the M's to go backwards. It sounds like an extremely painful process, but I think it's doable. Okay, so how do we interpret these M's? We do it as follows. So this is at level is equal to 0. This is at level is equal to 1.
Question.
Yes.
Last time, when we got these sigmas from the cylindrical thingies, there were some rules about what sigmas could be. Are there any rules about what the m's could be?
I think so.
I guess we will see.
I guess we'll see. Yeah. Okay, how do we interpret this? The 0 here will be interpreted as, so remember that our rules for pi and rho were that these were 1, 2, or 3 mod 5,
Mhm.
and these were 2, 3, and 4 mod 5.
Mhm.
And actually, these are precisely reading off that. Okay, so this is telling us that 0 elements are 1. There are 2 2s. Okay, I'm going to build pi down here. There's going to be 2 2s coming from this 2. And then there are 0 3s. And there are 0 everything else's. So pi is actually just straight up equal to 2. What about rho? There are 4 2s, because that's the first element here. 2, 2, 2. There are 2 3s. And there's 1 4.
Oh, no way. I see.
And then here on level 1, this
Yeah, you
is
add 5.
I add 5. So
I
now
see.
it's 2 symbols. And then an 8. And finally, in our case, because we ended with a field of zeros, C is actually 15. Okay. By construction, these are precisely the pi's and the rhos that we aim for. And given pi and rhos of this form, we can reconstruct the M table. So it seems like the M's can be arbitrary.
Mhm.
And then we just, toggle backwards and then fill in at the very corner, add back the M value from what's around it. And then we reconstruct this.
So the process of getting the M tables really eventually terminates?
Yeah.
I guess the maximum dude always goes down or something.
Okay. To finish the discussion. So finally, this this nu and this mu correspond to this pi, rho, and C.
I see. Okay. Naturally.
Okay, to finish the discussion, I want to run one more example of this toggle algorithm for another thing.
I want to do a quick sanity check.
Yeah.
Do all the numbers add up to the same thing? There's
Maybe.
8, 7,
Better.
7. The 4s line up and 2 3s line up. So there's an extra 5 3 2 2. But sorry, there's an extra 5 and a 3 on the mu nu side, and there are extra 2 2 2. Are we off by 1?
Okay, let's do it carefully.
I'm being really lazy.
Okay, 2 2 2.
You can also just add them all up.
Let's not do that. Oh shit. Okay, I have to keep the 2s. 3 3 3 3 8 7 7 8 7 7
And a 4. Ah, okay. Yeah, they all add up to the same thing.
Yeah, so it's actually extremely non-trivial that the toggle process gives us the same number as the total sum of the partition. This is actually a theorem in the paper.
That's kind of incredible.
Using and the proof was using generating functions. So by magic, this bijection, actually works. But from an algorithmic standpoint, this is just a bijection. Okay, so let's close off with one last example. But we do the whole process again with another with another partition. Okay. Okay. Let's see. Okay, here it is. 10, 8, 4, 3, 5, 4, 3. Okay, let's try to do it.
This is gonna take a while.
It is. Um, 3. And the focus is okay. Let's do this.
Should we reset our M table?
Okay,
Wait, I'm still confused. Where did the mod 5 come from?
I don't know.
That was just like a rabbit out of the hat.
Yeah, absolutely.
Okay. It's all right. I will accept it on faith.
Yeah. Where did it come? It might have something to do with the cylindrical partition business. 3 plus 2 does actually equal 5.
Good point.
I don't know if that's where the 5 comes from.
Yeah, but this 1, 2, 3 mod 5, 2, 3, 4 mod 5, 3 columns on the M table. It's kind of mysterious.
Agree. Absolutely.
It very much feels like we tried it and it worked.
Yeah, this took actually a really long time to discover. So this paper
Yeah, no kidding.
was in 2017, and Rogers published it in like 18 something something.
Oh my god.
And for basically the entire time, the only proofs we've had were by generated function or similar technology. And so somebody, well, I should attribute this to somebody. And this is all found in a paper called Corteel. Okay.
So you mentioned that the generating functions are used to prove that the toggling thing is terminated. Is this really just like an algorithmic interpretation of what you're doing with generating functions?
I think so the toggling is somewhat new. There's something called RSK. This is like one of the foundations of algebraic combinatorics. It's some algorithm that relates permutations or matrices to Tableau, so things that look like the Young diagrams that we made fun of earlier. And there's something called an insertion algorithm for RSK. That was how it was first written down. And maybe in 2014 or something, there was it was discovered maybe that there's a local sort of transformation rule for RSK. So the insertion algorithm is kind of global. You work with lots of boxes at the same time. You have to have the whole picture. Whereas the local transformations, as you saw, were just based on a neighborhood. And it turns out that the local transformation in question for RSK is precisely the toggle loop. So I do think it's somewhat recent. So that is not immediately clear from generating. So I didn't look at a single generating function while reading this.
I see.
Okay, let's get to work. M is 0. Let's toggle 5. This becomes a 6.
Oh no. Shouldn't we use the 4
It
below?
becomes a 7.
Yeah.
Very good. What about this guy?
That should be a 3.
Yeah, this becomes a 3.
And all the zeros stay zeros.
All the zeros stay. Okay.
Do we need to update the? I guess we don't. Yes, we do.
There's a 3 down here, right? Yeah. Okay. I don't think it actually matters, but to be safe.
Wait, is there a 3 down there?
No. Wait. Yeah, because it's 7, 10, 7, 4, 3, 3, 2, 10, 7, 4, 3.
Okay.
No.
Wait, no, I'm confused. What did you start with?
I started with this. And the 3 popped up because of
Right. Sorry.
And this 3 is the same 3 as yeah. Okay. Who do you want?
8.
8. So M is 1. Right. Then I'm attacking this guy next. This guy's toggles to be a 3. This guy toggles to be a 3.
Mm-hmm.
Don't worry.
Everyone is 0.
Okay.
Get the 4.
At the 4. M is 1. 4 minus 3 is 1. It's gone.
That 3 doesn't toggle.
This 3.
Mm.
This 3 doesn't toggle. Okay, nothing happened.
Shouldn't that 0 become a
Oh yeah.
2?
Yeah, you're right.
And then everything else is chilling.
Okay. Moving on. Keeping our anchor points. Okay. 10. M is 3. Oops. Wrong place. 3. By 10.
That 3 doesn't change.
This 3 doesn't change. This
Was a 0, now is a 2.
that was, yep.
And then everything else is there.
Yeah. Right.
There should be one more 2. 4 spaces below the 7. Other 7.
Others.
Other 7.
Very good. 7 next, right?
Yeah.
So there's a 4. And then I'm attacking this guy.
That
Okay.
stays
That stays the same.
That's a 3. That's a 2 now.
It's a 2 now.
And then everything else. Yeah.
Is it in the wrong place?
Yeah, that's in the wrong place.
Okay.
Yeah. Yes. And then the last entry in the M table is 0. And yeah. But we have to keep going.
Are there toggles?
Yeah.
This toggles to a 2.
Yeah. And then
This
the next 0 also becomes a 2.
Okay. There's a 2 here. What's over here?
We're not diligent in updating that. But we can. I mean, we have the fundamental domain here.
Yes. Okay, so there's lots and lots of 2s down here.
Yeah.
4, 3.
The 4s
2,
should all be gone.
Yeah.
There should be no more 4s.
Yeah. That's it, right?
I think so.
Okay.
We might run out of board.
I'll write smaller.
Oh, very good.
Okay. Let's check to make sure we're on the correct spots. It seems like we're making good progress. I'm a little suspicious.
Is our M table different from the reference?
There might have been a 1 here. Or there might not have been. We'll have to see. No, there isn't a 4. We're good. We're so good.
Mm-hmm.
We're cooking.
We are.
Okay.
Cooking with the gas, as they say.
Okay, we'll continue. Okay, here is the fundamental domain.
Yes.
M is 0.
Yes.
This 3 goes away. This 3 goes away.
I feel like I'm not doing much.
Well, you're checking our work. Without you, I would have already made 20 mistakes. Oh. Okay.
So that 2 toggles to a 3.
Yeah.
Mm-hmm.
Okay. do we need to update any people here? And there's a 2. Okay. Next, 5 more to go, and then the thing stabilizes.
Does it become just all 2s?
It does.
Oh.
And then C will be taken to be
10.
10, comma 10. Yeah, we'll see.
We'll see when we get there.
We'll see. Yeah. Don't worry about it. Okay, let's keep going. 0.
Mm-hmm. Now I know that it stabilizes to all 2s.
This is a 3 now.
Yeah. And then the 0
is a 2.
Is a 2, and then it's 0. Yeah.
And then there's some 2's down here.
Yeah.
Okay. This is a 0. And this becomes a 3.
Ish.
Okay. Let's have faith. I think something's gone wrong. No, we're fine. Okay. M is 0.
Okay.
M is 0. This guy becomes a
2, yeah. Yeah, because the 2 above and the 2 to the right.
Yeah. I think we may have prematurely toggled some things. I don't know.
Shoot.
We'll see.
Like you missed a 2 in that corner. Because
Sure.
the 0, yeah, that should have flipped to a 2.
Okay. This 3 still is a 0. Okay. And this stays a 2, this becomes a 3.
And then that 3 also goes to 0.
This 3 also goes to 0. I think this is where we made a mistake. This probably had to be a 2 at some point.
Yeah, it does say it's a 2 up there. So
well, because we didn't update it. So I think we definitely botched this somehow.
How did that even become a 3?
How did it become a 3? It was based on a toggling here.
I see.
But was there a 2 here?
Oh, that 3 should have been a 2.
This 3.
Yeah, because look.
No, this 3 is this 3.
What?
Really? No, this. Yeah, that 3 is this 2.
Wait, right. Then what is that? Yeah.
So somewhere along the way we made a mistake. This was actually supposed to be a 2. And now M is 1.
Amazing.
Okay. And now everybody's a 2.
Okay.
All the 3's disappear.
We're gonna
erase the bad evidence. And now we have a sheet of 2's. Okay. And
I see. So the 2's will give only 0's for the M's and then spread more 2's.
Yeah.
As you toggle.
Yeah. And all of the diagonal. So if we look at this shape again, this diagonal, this diagonal, this diagonal, this diagonal, this diagonal, they're all 2's. Okay? So these are called lambda, remember. And so lambda is equal to 2, 2. All the lambdas are equal to 2, 2 because of stability, right? Well, the theorem.
Isn't one of them going to be a 2, 2, 2?
No, this can't be.
You're right. I'm sorry.
Partially because I know the answer.
Yeah. I'm sorry.
And I think we did everything correctly except for botching this. Yeah. Okay. And finally, we are ready to write out pi, rho, and C, and then and the and the computations.
Amazing.
The torturous computation. Okay. So what's pi? You just read it off from here.
Just 2 and 3.
That's right. It's 3, 2. What's rho?
It was, I guess, sorry, 9 and then 2, 2, 2, 2. And Oh, sorry, 9 3 3 3 3. Yeah.
And finally, C will be 5 times 2, 2.
Very good.
So it does seem like 5 is related to the fact that 3 plus 2 is 5. That is what causes the sums to be the same, because the total sum in this fundamental domain is precisely the sum of this one diagonal plus times 5. Okay, so that explains the 5. I think.
I see.
With that, I think we're done.